Test, test. Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program at the University of Ontario Institute of Technology, also known as Ontario Tech University. I also took my Bachelor's of Science in Pharmaceutical Chemistry at this institution as well. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then just visit the links in the description below. Okay, so I'm going to get started with the first set of questions. Okay, so the first question states, in each reaction box, place the best reagent and conditions from the list below. So just analyzing the reaction so far, we have just two carbons with a triple bond, and then they form this structure that has more carbons than what it started with, and also two bromine groups. So I'm just going to write this down. Question 1. Okay, so we need to use a reagent that will be able to attach new carbons onto this triple bond. And we also want to end up reducing this triple bond in the end, since they're all single bonds in the final product. So first, I'm going to be using sodium amide. I'll just explain why in a bit. Okay, so when you react this sodium amide with the triple bond, you get this acetylide ion. So this is actually an excellent nucleophile. And what it does is that it's able to react with alkyl halides to form new carbon bonds. Okay, so that's step 1. Just gonna label these as A and B. So that was A. So then after, we have this acetylide ion. And then from there, in our final product, we add 2 new carbons. So therefore, we can use just this ethyl group with the bromine there. And then we're left with this structure. Okay, so we have successfully added our new carbons, and now we want to somehow add in our bromine groups. So to do that, we also want to reduce our triple bond as well. So we can actually add 2 equivalents of HBr. So the first equivalent will reduce the triple bond to a double bond and also add a bromine onto one of the carbons. And then the second equivalent of HBr will reduce that double bond into a single bond. And that's how you would attach your 2 bromines. Okay, so and then we're left with our final product. So this is a 2-part question. So I'm just going to start this on a new page. So this is still question 1. Continued. Give the correct organic products in any order for the following ozonolysis reaction. Okay, so we have this hexane, and at the top we have this double bond. And then with these conditions, this is known as an ozonolysis reaction. Okay, so let me write down what the ozonolysis reaction is. Basically, this reaction produces carbonyl compounds. So by carbonyl compounds, I mean either ketones or aldehydes. And then first, your O3 forms an intermediate with the double bond alkene. And then next, the zinc reduces it. Okay, so it's actually pretty easy to figure out what the products are from this reaction. Wherever you see the double bond, I kind of just like to draw like a line that breaks it into 2 different species. And then wherever the line broke, you just replace it with either a ketone or an aldehyde. So the first product will look like this. And then the second product will just be this ketone. Okay, so you can see, I'll draw an H here. Wherever I drew the line to break the double bond is where the new aldehyde or ketone would form. Okay, so let me just confirm with the answers here. So from question 1A, would use the sodium amide, and then the ethyl bromine. I think they might have used an extra carbon there. Yeah, so the second one should just read CH3CH2Br, but then the HBr to equivalence is correct. And it doesn't look like they answered question number 2, so I'm just gonna write it in. Okay, so I just said the sodium amide and 2 equivalents HBr correct. You should use CH3CH2Br in the second step. For the second part of the question, the starting product will separate at the double bond, forming 2 new products containing carbonyl groups in its place. Okay, so on to question number 2. Draw a structural formula of the R configuration of the compound shown below. Okay, so let me just write down this compound. So we use the wedge/hash bond tools to indicate stereochemistry. Include hydrogen atoms at chiral centers only. If a group is achiral, do not use wedged or hashed bonds on it. Okay, so the first thing you want to do with these types of questions is to first find the chiral center. So that just means it's a carbon that has 4 different groups on it. Okay, so if we draw in a hydrogen atom just over here, then we know that this carbon in the middle is the chiral center. So after you find that, you want to find out the priority order of all these different groups. So you give first priority according to the atomic number. and then the lowest priority. So most of the time, it's usually the hydrogen atom. It's placed at the vertical position. Okay, so I'm just going to rank them on here. So the CH2OH group is given the highest priority. This is a 1. Then second would be the group containing the nitrogen. The third is this R group. And then lastly, hydrogen is the lowest priority. Okay, so I'm just gonna redraw this. Down here, just to show the stereochemistry. Okay, so I have my lowest priority sticking out like that. I'm just gonna number them again. 1, 2, 3, 4. And then if you were to look at the direction of the numbers, it kind of goes in an anti-clockwise direction. And this is what we want for the R configuration. Okay, so let's double check our answers. Given the structural formula, I think they drew it as S configuration. But they found the correct chirality center and they labeled it correctly. It's just a matter of positioning your groups so that it moves in the right direction. So they also drew it anti-clockwise. So I'm just going to say that priority that's like half right, since we need to draw our configuration. Priority order is correct. Need to draw an R configuration instead of S. So the words look right. Okay, so on to question number 3. Determine whether each of these processes is reversible or irreversible. Okay, so we all know that when you have an irreversible process, this basically means you can't go back to your starting position. And then the opposite of that is reversible. That's pretty straightforward. I'm just gonna make like a graph table. And then we'll go through all the different options. Okay, so solid melting, infinitesimally slower at its melting point. I don't think I said that right, but basically when any phase change is happening at the melting point or at the boiling point, it's still a reversible reaction. Since you're still at that same temperature, you can go either back or forth. So I'm going to say that 1 is reversible. A single swing of a real pendulum. So when you have a real pendulum, I'm just going to write that this is irreversible, and I'll just say y down here. So when you have a real pendulum, every time it moves like this, a small amount of energy is used against the friction forces, so therefore you can't go back to the original state. Just gonna write that down. And go back. So that's why this is an example of an irreversible reaction. So the gas condensing infinitesimally slower at its condensation point. So again, it happens at the condensation point, so it's still a reversible reaction. Solid melting slowly above its melting point. Okay, so unlike the other two, you're already above its melting point, so it's irreversible at that for this process. Liquid freezing below its freezing point. So again, this is an irreversible reaction. Liquid freezing slowly at its freezing point. So since it's still reversible. A single swing of a frictionless pendulum. Okay, so unlike the real pendulum, there's no friction involved in this frictionless pendulum. So therefore it's able to swing and still go back to its same spot. So in this case, the frictionless pendulum is reversible. Liquid vaporizing slowly at its boiling point. This is reversible. Gas condensing below its condensation point. That's irreversible. And then liquid vaporizing above its boiling point is irreversible. So let's double check our answers. A reversible process is one whose direction can be reversed by inducing minute changes to the property of the system. Irreversible cannot return to the initial system and surroundings. So they said 1 was reversible, 2 irreversible, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this solution is correct. Okay, so on to the next one. Okay, so question number 4. What is the Ka reaction of HCN? Okay, so first I'm going to write the dissociation of HCN and water. Okay, and then The reaction looks like this. So usually it's your concentration of your products over the concentration of your reactants. And also you don't have to take into account liquid water since its activity is just 0. So I'm just going to write it down here. So the concentration of your products over the concentration of your reactant. Okay, so that's for A, the Ka reaction, and B says the Ka is equal to 6.2 times 10 to the minus 10. Then what is Kb? For Cn at 25 degrees Celsius. Okay, so here we can use the relationship that Kw, which is 1 times 10 to the negative 14. So this is a constant that's given at 25 degrees Celsius. So I'm just going to write it here. And then we can rearrange this equation to solve for Kb. And then just plug in the values. Ten to the negative 14 over 6.2 times 10 to the negative 10. And then you get a Kb value of 1.61 times 10 to the negative 5. Okay, so let's double check our answer. Okay, so they just, yeah, so it's the same answer, except they did 0.16 times 10 to the negative 4 instead of 10 to the negative 5. Yeah, so that should still give the same thing, if I'm not mistaken. So on to question number 5. How many unique HNMR and CNMR signals exist for each compound? Okay, so I'm just going to write down each one. So this is A, B, I'll do the other two down here. Okay, so when you want to find out if how many unique signals there are. Basically, you want to see if your protons or your carbons are in the same environment or not. So you want to look at their environment and also their neighbors. So like whatever they're attached to see if it's the same or if it's a different neighbor. Okay, so first for A, I'll do the HNMR signals in green. So you'll see that these two hydrogens are in the same environment, and also these two hydrogens are also in the same environment. So therefore this one gives off 2 HNMR. And then we can do the next one. So this hydrogen, if you look at its neighbors, it's beside like a single proton and also beside another CH3. This CH3 is beside 2 CH3s. This one is beside a hydrogen up here. And then another CH3 on that side. So you can see that these are all different environments. I'm just going to try to draw them in like different shapes. So therefore this gives off 4 HNMR signals. And for this one, you'll see that again, these two hydrogens are in the same environment. And then these two hydrogens are in the same. So this gives off 2 HNMR. And then for this one, all of them are equivalent with each other. So this only gives off 1 HNMR signal. Okay, so then we're going to do the same thing, but with our carbons. So here we have a carbon connected to 2 hydrogens, double bonded to another carbon. We have a carbon connected to 2 carbons, well, 2 methyl groups and another carbon. And then these 2 carbons both are connected to a double bonded carbon and 3 hydrogens. So therefore this gives off 3 13 CNMR signals. Okay, so we'll do the same thing for this. All of these carbons are different from each other. So there's going to be 5 CNMR. For this one, these 2 carbons are the same, and then these 2 carbons are both connected to a proton and a methyl group. So you'll only get 2 CNMR signals. And then for this one, these 2 carbons are the same, but they are different from the carbons that are in each methyl group. So you see 2 CNMR signals. So let's check our answer. So they got 2 and 3 for the 1, 4 and 5 for compound B, 2 and 2 for compound C, and then 1 and 2 for compound D. So great answer. They also added like the actual values as well, so that was pretty cool. Solution was correct. Okay, so this is question number 6. Draw the major organic product for the following Friedel-Crafts acetylation reaction. So with Friedel-Crafts, you start off with this benzene ring. Then we have this long carbon group. Okay, so I'm just going to rewrite this so that you can see what this structure looks like. 1, 2, 3, 4, 5 carbons. 1, 2, 5. Oh, sorry, it's only 4. And then the last one's a chlorine group. So 1, 2, 3, 4. And then there's a double bonded oxygen. So basically with Friedel-Crafts, wherever the chlorine is where it will attach onto your benzene ring. So since there's nothing on this benzene ring, you can just stick this group over here. Okay, so 4 carbons, and then this is your final product. Let's double check our answer. Yep, okay, so they wrote in the mechanism as well, so that's good. And let me just verify that this is correct. Okay, so on to question number 7. Sort these nucleotide building blocks by their name or classification. So you have phosphate, ribose, deoxyribose, purine, and pyrimidine. Okay, so let's rule out the phosphate since it's the easiest to identify. So it's the only one that has the phosphorus in it. This is your phosphate group. Then we're going to draw our ribose, which is this 5-membered ring. So you'll see there's 2 5-membered rings, but ribose is the one that has the extra alcohol group on it. I'm just going to write that down. So I'm not going to draw out the hydrogens so that you can see. And then basically deoxyribose has like a similar structure. But it's missing that alcohol group. So let me write that down. Missing OH group. Okay, so next we're going to classify the rest of them as either purines or pyrimidines. Change the color. So basically with your purine, there are 2 rings involved. And then with your pyrimidines, there's only one ring involved. Okay, so let me draw all these groups. So first I'm going to look at the structures that have 2 rings and draw them out, hopefully neat. This is fine. Okay. So if you're familiar with your biochem, you'll see that these are part of the building blocks of DNA. So these are guanine and adenine molecules, and they're both purines. And for the pyrimidines, I'm going to look at all of my one ring structures. So there should be 3 of them that are left. And lastly, okay, so again, you'll notice these as uracil, cytosine, and thymine, which are your building blocks for DNA and RNA. Okay, so let's see what they said. Phosphate, ribose, deoxyribose has a removed oxygen. Pyrimidines have a 6-membered ring, and then the purines have a 9-membered double ring system with 4 nitrogens and 5 carbons. So solution is correct. Okay, so now we're on to question number 8. Complete the drawing of the product of the Diels-Alder reaction, ignoring stereochemistry. Okay, so we're ignoring stereochemistry for this one. And they just want us to write out final product. So you'll notice that these structures have a whole bunch of double bonds. This one has 2 benzene rings. Then this bottom one looks like this. Okay. And this is the Diels-Alder reaction. Okay, so let's take a look at our products, our reactants. So here you'll notice that this is a diene group. That just means it has 2 double bonds. And then this triple bond in the middle, 2 like carboxyl groups, is called a dienophile. And basically, this is a very good electron withdrawing group. And what happens in the Diels-Alder reaction is that it's basically a cycloaddition reaction. And I know that they said to ignore stereochemistry, but basically this reaction occurs in the S or cis form. And this is required because if it was like in the trans form, then it would be too sterically hindered. Okay, so basically, back to the question. At 420 Kelvin for 5 hours, get a final product that looks like this. Okay, so first I drew out the group here, which is the dienophile, and basically kind of connects to your diene to make a new 6-membered ring. And then the groups on the side stay the same. Okay, so this is our final product. I'm also gonna circle the part that like kind of connected together. So those are the new bonds that were formed. And if we look at our answer here, it's the same thing except upside down, but it's still correct. Solution is correct. Okay, so I think we have time for one more question. I can see already that it's just this large molecule that I'm gonna have to draw in here. So select all of the chirality centers in the structure. Okay, so bear with me while I draw this all out. Okay, so it's a very large molecule. Okay, so let's draw up here. So that connects to here somehow. It's just a very large ring. Alcohol group there. Okay. I'm gonna draw this on the carbon right there. Okay, so this question looks like it would be overwhelming, but we can just break it down together. Okay, so what they mean by chirality centers, one of the main definitions is that the mirror image is not the same as the original. And also with chiral centers, there should be 4 different groups, which I mentioned earlier in this session. And another thing that'll help us is that the carbons with double bonds are also not chiral. Okay, so I'm gonna circle all of them in red. So we can rule out all of the benzene rings from not having any chiral centers. And we can also rule out all the carbonyl groups because they have double bonds. So if we look over here, this would be an example of a chiral center. It has 4 different groups and a hydrogen, which is not shown. The same thing goes for this carbon, 4 different groups. Spot one over here. This one has double bonds, and then these ones are the same. So this is also an example of a chiral center. And then the carbon that's connected here is one as well. Okay, so this one has different groups. Same with that. And then also this one in the middle. So this one has 2 hydrogens that you just can't see, so I'm just going to write that in. This should be CH2. So that one is not. Okay, so this carbon has a double bonded oxygen, so it's not a chiral center. All of the carbons that are at the end here are connected to 3 hydrogens, so we know that that is also not a chiral center. Same goes for that one. This one also has 2 hydrogens, so that's not one. So the carbon connected here has an oxygen, a hydrogen, and then 2 different R groups, so that is a chiral center. The carbon here has an oxygen, a double bonded carbon, and then another one there. So this is a chiral center as well. Then we can rule these ones out. And then I think we're back at the beginning. I think that might all be it. So let's count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 chiral centers. So let's check our answer here. Yep, so this person also drew it out very neatly and counted out the same 11 chiral centers. So this solution is correct. Okay. So I think that's all we have time for today. If you like today's Q&A and you wanted to be notified of when we do this next, then hit the subscribe button and notification bell below. And if you enjoyed this video, go ahead and give it a like and comment, and share it with all of your friends and classmates. This has been Donna from the OneClass program, and I hope to see you soon. Bye.